So today we're going to be talking about apparent power and power factor. And when we ship power, when we transfer power, let's say from the company, the power supply company, to your home, power is going to be lost along the way. We will lose some of the power. So that will get us to something called the power factor. What percent of that power are you getting? So first let's define what is the apparent power, and that is how much power is the power company supplying. So apparent power, we're going to define the apparent power as, well, let's take the average power first. If you have a voltage source, V equals, has some maximum value, cosine WT plus theta. And you have a load across that, so you'll have a current going through that, which is I max cosine WT plus phi. That WT will be the same. You saw that from the previous examples. Now, if you remember the average power, we calculated the average power last time to be what? 1/2 V max I sub max cosine, what was it? Theta V, I call it minus theta, or theta minus V. Sometimes I call it theta V minus theta I. So it's theta, which is the phase shift of the voltage minus the phase shift of the current. I don't like theta and phi, so I usually call them 1/2 V max I sub max cosine the voltage phase shift minus the current phase shift. So I like this one better instead of theta minus phi. Now, 439. We're going to be talking about apparent power. So let's define what is apparent power. And by the way, the units for apparent power we use, just before I forget about them, is volt ampere. That's how you know if you have apparent power or something else. The unit for that will be capital V, capital A.
Sounds very similar to watts.
Apparent power is calculated, we'll use, I'll just write apparent power for now. It's calculated by using the equation 1/2 V max I sub max. That's because apparent power, the true power, assuming there's no phase shift, that's the maximum you will have when the cosine theta V minus theta I is 0, cosine of 0 is 1. So it's 1/2 V max I sub max, or if you're using the RMS value, effective value, it's V effective times I effective, or RMS, whatever you want to call it. That's known as the power factor. By the way, this equation, if using the RMS value, this equation becomes what? V effective, I effective, or RMS, I use either one, cosine theta V minus theta I. This is the average power delivered to the load. This is the power supplied by the source. This is what the power company is sending you. This is what you're getting. If you have a perfect home, theta V minus theta I will be 0, and the cosine of 0 is 1. You're getting exactly what the power company is sending you. But you'll never get that. You get a portion of that. What you get is called the power factor. And power factor is defined as the average power divided by the apparent power. And the average power is actually what? Using that equation, V effective, I effective, I can use either one, cosine theta V minus theta I, divided by the apparent power, which is what? V effective, I effective. And if you do the math, what will happen to V and I? They cancel each other out, and the power factor is known as cosine theta V minus theta I. That's your power factor. Now again, if your load is purely resistive, I'll put on the next page. I'll wait till you finish writing. So this is the average power delivered to the load. It could be your washing machine, could be your stove, hair dryer. This is the apparent power, the power supplied by the power company, electric company. That's the apparent power, that's the load power. The ratio of them is the power factor. What are you getting?
Why does it have different units?
Which one?
Apparent power.
That's how we differentiate between them. That's how you know which one's which.
So technically they're both watts.
This is in watts here. This is always measured in volts, ampere. The apparent. So you'll know when you look at when someone gives you a problem, you know if that's apparent power or is given to you in average power.
So they technically have the same units, right? Because full ampere.
Well, this is mathematical. This is unitless. So these are the same units, yes.
Okay.
But we always refer to this in watts. Otherwise, you wouldn't know that's an average power or an apparent power.
Okay.
Now, if your load is purely resistive, so for a purely resistive load, that means there is no capacitors, there is no inductor. If your load is purely resistive, you're going to find out that theta I really equals theta V. There is no phase shift. So the power factor in that case will be what? Cosine of 0. The difference between them is going to be 0. And what's cosine of 0? It's 1. So you have a unity power factor, a value of 1. For a purely reactive load, that means a capacitor or an inductor, that means theta I, it's either going to be plus or minus. It's going to be actually theta V plus or minus either 90 degrees. I should write them that way. Theta I is always theta V. It's either plus or minus 90 degrees. So the power factor for them is going to be either cosine plus or minus 90 degrees when you subtract the two values. Theta V minus theta I, when you subtract them, it's going to be plus or minus 90 degrees. Well, either way, what's cosine plus 90 degrees or cosine minus 90 degrees? Cosine of 90 or minus 90 is 0 degrees. You have a power factor of 0. Now, when we start talking about power factor, you're going to hear two terms: leading power factor and lagging power factor. So power factor is going to say leading or lagging. How do you know it's leading? That's when theta V minus theta I, the difference between them, it's bigger than negative 90 degrees and less than 0. So you have a negative value. Theta V minus theta I, it's negative. That's a leading power factor. Your power factor is going to be lagging. That means theta V minus theta I is going to be greater than 0 and less than or equal to what? 90 degrees. So when you have a positive value here, the power factor is lagging. When it's a negative value, the power factor is leading. And if you know it's lagging or leading, you know if you have a load that is an inductor or a capacitor, we use something called Eli, the Iceman. We use E for voltage instead of V. So E is the voltage, I is the current. L is what? Inductor. So in the inductor, who comes in first? Voltage, bless you, before the current. The voltage leads the current. When you say what is the power factor, the relationship of the current to the voltage. So the current lags the voltage. So the current lags the voltage. C is the capacitor here. I is the current. So the current leads here before the voltage. So we talk about leading or lagging power factor. So leading or lagging power factor, leading / lagging power factor. We're referring to the phase of the current with respect to the voltage. So it's always the current with respect to the voltage. Notice in the inductor, the current lags the voltage. In the capacitor, the current leads the voltage. So when they say we have a lagging power factor, go lagging power factor. Oh, we have an inductor load. When they said the current, the power factor is leading, oh, we have what? A capacitor on the load, not an inductor. Here's an example. Let's put them together and take an example. And see if it makes sense. But remember, Eli the Iceman. That'll let you know who's leading, who's lagging. We have this circuit. I'll give it to you in phasor already. 60 angle 0. And I'll give it to you in RMS. That's RMS, effective value. Make my life easy. Here that Z Thevenin, 2 minus 1J. The load is 1 plus 5J. Now let's look at the load. 1 plus 5J. Inductor plus let's calculate the average power delivered to each of the loads. So we're going to calculate the average power to this, the average power to that one, and the apparent power supplied by the source. We need to calculate all of them. Well, let me find I first, so I can define I as the current going through it. And using Ohm's law, I equals the voltage source, which is what? 60 angle 0, divided by the sum of these, which is what? 3 plus is a 4J. And if you do the math for that, the current will be what? 12 angle negative 53.13 amps. And this is RMS. Why? Because the voltage was RMS. Okay. If you remember, actually, the average power, just refresh your memory, we said the average power absorbed by any of these is what? VRMS, IRMS, times cosine theta V minus theta I. Or we can use IRMS squared times what? What is R? Because the inductor and the capacitor have absorbed zero average power. So it's really IRMS squared times R. Only the resistor is going to absorb the power. So let's call the load here, I don't know, what should we call this? Load 1, load 2? What is the average power absorbed by load 1? The top one. It is I RMS squared times R. And what is my RMS for that one? Is it 12? So it's 12 squared times 2. The capacitor will absorb zero power. Do the math. 144 times 2, is that 288? And the units for average power is always watts. As a capacitor, average power is 0. Same thing right here. The inductor absorb an average power of 0. So only the resistor. So the power by load 2, you can actually find what the voltage here cross that, which is you take this current, if you want to do it the long way, and multiply it by that, and you'll get theta V minus theta I and use that equation. But I'll be just wasting my time. By load 2, the average power is IRMS squared times R again. 12 squared times the 1, which is 144 watts. So that's the average power taken by each load. Now, let's find out what is the apparent power. Apparent power is the power supplied by the source. We said V effective or RMS times IRMS. My voltage is 60. My current is what? 12. What is 60 times 12? Is that 720? 720 VA. The units for apparent power is VA. Let's see if we can calculate the power factor. We didn't ask for it, but while I'm at it, let's calculate the whole power factor for the whole system here. The power factor is the average power over the apparent power. How much power was supplied to both of these together? 288 plus 144. And what was the apparent power? 720. So let's see if we have a calculator for that. $288 plus 144, 432 divided by 720. Not a good system. You're getting 60%. Your power factor is 60%. So the power supply is sending you this much power. A box full of power. You're only seeing 60% of it. So 40% of it is going to waste. You're paying for it, but you're not getting that. Can we fix that? We can. We'll get to that later, which is by adding a capacitor to actually fix that. Let me take another example. Let me see if I can find one in the back of the book. Okay. Here's my problem. Another example. Let's assume that W is equal to 40 rad per second. And we have this circuit. We have a current source of a value 275, angle 20 milliamp. We have a resistor of 1 ohm here. And we have a load. And the value of the load here, the impedance of that is 50 angle minus 100. Notice that's a negative value, negative angle. That tells me actually what we have. Capacitor. A resistor and a capacitor, RC. Calculate the instantaneous power delivered to the load. Oh, that's a 1K, I think, not 1 ohm, 1 kilo ohm. Delivered to the load. Instantaneous power, okay. The average power delivered to both, meaning I say both to this, and the power factor at which the source is operating. So there's a lot of stuff. Instantaneous power, I can find the voltage and the current through that and calculate actually what the instantaneous power. You tell me what time, I'll tell you what the value. I can figure out what this current, let's call this I1 and I2. So let me focus first on instantaneous power. And that's equal to what? The voltage times the current. And I want to find the instantaneous power through this one. I'm not going to do both. That's too much work. So let's say this is my load. I'm only interested in instantaneous power in that one. Really, it's not a big deal for this one too. Once you know what that current and this current, you know the voltage across each one of them in parallel, and you multiply the two. I make it sound like it's a lot of work, but it's not. Just a few extra steps. So what is I sub 1? What's I sub 2? You know what? I'll do both. I sub 1 is going to be current division. 275 angle 20, that's milliamps, so I'll make that 0.275 because it's in milli. 0.275. If I want to find I sub 1, I got to use what? 50 angle negative 100 over 50 angle negative 100 plus 1000. Current division. And let me just pull my calculator out. I got a 0.275 angle 20 times 50 angle negative 100 divided by 50 angle negative 100 plus 1000. If everything goes well on my calculator, I got 0.0132 angle 1.657. Let me just double check one thing. I didn't look to see if because I use this calculator for everything to see if I'm in degree or radian mode. Oh, I was wrong. I was actually in degree radian mode. I got to redo it. I forgot that little detail.
But you need to be in degree or radian mode?
This is in degrees.
Oh, we need in radian.
You need to be in degrees.
Oh, you
Yeah,
need to be
I
in
got
degrees.
that.
Because I got that in degrees.
Yeah, that's negative 77.1 for it. The first number was good.
Yeah, the answer would be, but the angle is the angle correct.
Oh, okay. Yeah, we got it. I got negative 77.
Yeah.
So what was it?
0.013.
What?
Angle negative 77.2.
0.2 degrees, yep. And let's find I sub 2 while we at it. It's 0.275, angle 20. If I'm looking for I sub 2, I'm going to use the 1K on the top. The bottom is going to be what? 50 angle negative 100 plus 1,000. Remember, 1K is 1,000. Maybe I'll put 1,000 instead of 1K so you don't make a mistake by putting 1 there. So here we go. 0.275 angle 20 times 1,000 divided by 50 angle negative 100 plus 1,000. And I came up with 0.277 angle 22.8. Is that what you got? Okay. Can we find the voltage? Well, all three are in parallel. You can find the voltage. The voltage across them is going to be I sub 1 times 1K. What's I sub 1? Here we go. It's 13 angle negative 77.2 degrees. So you want to find the instantaneous power by the 1K as a function of time. It will not be, it's going to be what? Voltage times current. What's your voltage? 13 angle negative 77.2. Well, actually, I got to convert that to cosine, right? So because I'm going as a function of time. So in terms of time, this will be what? 13 cosine, W was 40t, but now I got to convert this 77 degrees to radian, because that's in radian. So I got to take that multiplied by pi divided by what? 180. So negative 77.2 times pi divided by 180, negative 1.35. That's good enough. And this one will be 0.277 cosine 40t. And let me convert this one to radian. 22.8 times pi divided by 180, 0.39 or 0.40. This will be 0.013 cosine 40t minus, let's try that, I just did that, the 77 was what, 1.35? So that's going to be 13 cosine 40t minus 1.35, and times I sub 1, that's this one, the 1K, I sub 1, that's the I sub 1, that's V1. I sub 1 is what? 0.013 cosine 40t minus 1.35. The good news, the cosine are the same, right? The cosine is the same, so multiply 13 times 0.13 13 times 0.013, 0.169 cosine squared 40t minus 1.35. You tell me what t is, and I'll tell you what the average power delivered to the 1K ohm. We can do the same thing with that one. Multiply the two of them and just write the answer. So that's instantaneous power to the 1K. You want to find the instantaneous power for this? Multiply them out. To the 50 angle negative 100, we know what the current is. I'll just leave it without simplifying. I sub 2 is what? 0.277 cosine 40t plus 0.40 times the voltage, which is what? 13 cosine 40t minus 1.35. Again, you tell me what time and I'll tell you. For the source, you got to convert that to rectangular, to time domain, and multiply that by the current going, the voltage. So in time domain, this will be what? 0.275 cosine what? 40t, and let's convert the 20. That's 20 times pi divided by 180. 0.35. So the source now, the average power by the source is going to be the voltage, which is 0.275 cosine 40t plus 0.35 times the voltage, which is what? 13 cosine 40t minus 1.35. So we found the instantaneous power for each one of these. You tell me what time, we can calculate it. I didn't care about that part. So let's get to the average power and the power factor. Take your time. I'm in no rush. So now, what is the average power delivered to the 1K and the load? Since the 1K is purely resistive, is going to be what? We know the current, IRMS squared times R. What is IRMS? I sub 1 is what? 0.013. Squared times 1,000. .013 squared times 1,000. 0.169 watts. Now remember, if you break this one down, this one here, the load, if you break it down, what do you have? You have, 50 cosine negative 100 plus j 50 sine of negative 100. So let's see what the values are. 50 cosine of negative 100, negative 8.68, 50 sine of negative 100, negative 49.2 J. You see, how can a resistor be negative? You will see where we have negative resistors down the road as we advance in the course.
So does it make it do the opposite of resist? Pretty much?
No?
Or just direction?
Nope, nope, nothing to do with the direction actually, something else.
Not susceptance, conductance. No, that's EM.
No. We'll get to it, it's coming. So this will have a 0. That will have an average power. So what's the average power by the load? It's I squared RMS times R. So I is what? For that one is what? .277 squared times negative 8.68. Six, six, six. That's devil's number. Watts. Devil's number.
Does that mean we should decline the electrical company's offer? Or
Whatever they're giving you at that day, you don't want it. 666. Devil's number.
yeah, Is
Now-
that why we don't use negative resistors?
Hmm?
Is that why we don't want to use negative resistors?
Well, we'll get to them. You're going to encounter them, but not like there are no, in real life, there are no negative, actual resistors that are negative.
Right.
But that's something else. As we get down the road, I think chapter, I can tell you in a second.
Reactive.
Could be chapter, in our book, it might be chapter, I think 13. So a couple more chapters. Yeah. So now what about the apparent power? Apparent, it's the source, that's VRMS, IRMS, which is 0.275, that's the current. And the voltage, we figure that to be what, 13? .575, and that's VA. The unit for that is VA. So we got the average power, we got the apparent power. The power factor is what? The ratio of the average power to the apparent power. The ratio of the average power to the apparent power. If I thought about this for now, I probably would have made this positive just for now, just to avoid the negative value. I don't want to start with that, but it's all right. And the apparent power is 3.575. The average out power 0.169 plus negative 0.666. And we're not really doing well with power factor here. We're getting junk out of this. We're getting less than 20%.
That's because it's a devil's company.
666.
International trade.